Okay, this is MAT 175, Lesson 12, Section A.3, 4.2, and 4.3, Properties of Rational Functions. And first thing we're going to look at is the properties of rational functions. Think of a rational function like a rational number as a fraction. So a rational number is also in fraction, like a fraction form, where you have a numerator or a polynomial in the numerator and a polynomial in the denominator. So it's like a polynomial in fractional form, where P and Q are polynomial functions, and Q is not a zero. Okay, you can't have zero in the denominator because that's undefined. The domain is set for all real numbers except those where the denominator is equal to 0, where basically we set the denominator equal to 0 and then solve, and wherever we get x equal to, that's where we would get a 0 in the denominator, so we can't have that. And so that would be our restriction for the denominator. Like here, we have, we want to find the denominator, and so we would set x plus 5 equal to 0, and then solve. And so we would get x equals to a negative 5. So if we put negative 5 in here, we would get a 0. And so we would say that in set notation, set of all x values where x cannot be negative 5. So in interval notation, basically, here's negative 5, and that would be open because that would give us a 0, and so it's everything else but negative 5, and so we would have negative infinity, comma, negative 5, open, union, negative 5 to infinity. So basically that's saying the same thing as in set notation, except we have an interval notation. Okay, the domain for this one, we're going to set x squared minus 4. We're going to set that equal to 0. And so when we do that, factor it or use the square root method. Here we'll go ahead and use the square root method, and we get x squared equals to 4, and so we apply square root, but we have to put plus or minus there, and so we get x equal to plus or minus the square root of 4 is going to be a plus or minus 2. So what that means is you cannot have 2 and negative 2 in the denominator, or that'll give you 0. So therefore our domain would be set of all x where x cannot be negative 2 and x cannot be positive 2. So in interval notation, again use the line graph, and cannot, again, it's going to be open at negative 2 and 2. It's going to be, everything else is okay. Okay, so in other words, if, the way you can look at this is, where is x not okay? Well, we know it's not okay at negative 2, and we know it's not okay at positive 2. So those have to be open there. Everything else is okay except for those 2 points. And so that's going to be domain union. And then what follows? Negative 2 to positive 2. Open. And then union, positive 2 to infinity. You still have these points in between here. Everything else is okay except for negative 2 and positive 2. Okay. The next one, here we have an x squared plus 1. So if we were to look at that one, if we set x squared plus 1 equal to 0, right, and apply minus 1, we get x squared equals to a negative 1, apply square root, well, you get an imaginary number. So therefore, there are no restrictions. Now we're going to learn later on that anywhere where you see x cannot be, those are called those are also where the vertical asymptotes are. And so basically your domain is going to be all real numbers, or negative, just negative infinity to infinity, because we don't have any place where x is going to be 0 in the denominator. If we have a negative 1, then negative 1 gets squared and becomes a 2. So that's just going to be negative infinity to infinity. And so that's the set of all real numbers, is the answer for that. Okay, and then here for the last one, set 1 equal to 0, and we negative x minus 1 equals 0, and we get x cannot be positive 1. Or negative infinity to 1, open union 1 to infinity. Okay. And, alright, now here's an example of a rational function where we're going to be plotting, showing what the points look like. So here x is 1/2. And so if we were to put 1/2, if we were to put 1/2, let's say we were to say h of 1/2. So this would be 1 over 1/2, parentheses squared, so that would be 1 over 1/4. Flip and multiply the denominator, and we get 4 times 1, right? 4 over 1 times 1. We flip that denominator and multiply it, and we get 4 over 1 times 1, so that's 4. So here's 1/2, 4. Well, let's say that h were 1 over 100. Okay, so this would be 1 over 100 squared, and so that would be 1 over 100. Parentheses squared, so that would be 1 over 1 over 1, 0, 0, 0, 0. So again, we would flip and multiply that, and we would get 10,000. So the closer we get to 0, the further up, the higher up the point is. And so, but we cannot have 0 here because that's undefined. So all we can do is get closer and closer and closer and closer to that point. As we do that, this is going to get closer and closer and closer to our asymptote. This would be a vertical asymptote here at 0, but it'll never touch it. It'll never get to it. It'll just get closer and closer to it, and so on. And same thing with the other direction. And so the further out we go, if x was 10, this would be 1 over 10 squared would be 100. So at 10 it would be 1/100, and so it's going to get closer and closer and closer to the horizontal asymptote. Okay, so here we have 1 over x minus 2 parentheses squared plus 1. So it's like the last graph, but now it's going to shift. Well, it's going, instead of getting the asymptote here at 0, x is 0 and y is 0, now that asymptote is going, that center of that asymptote where they crisscross at, that's going to shift, right? Which way is it going to shift? It's going to shift to the right. How many? It's going to shift to the right 2, and it's going to shift how many? Up 1. And so here's our, like we could say that's our parent graph. And then there it is, the x minus 2 makes it the vertical asymptote shift to the right 2, and then up 1. And so here it is, it's riding closer and closer to that x equals 1, but it does not get to that, or y equals 1. Let R denote a function of x as approaches negative infinity, or as x approaches positive infinity, the values for R of x approach a fixed number L. So that would be our horizontal asymptote. And as x approaches some number c, as it approaches infinity, the line x equals c is a vertical asymptote. So the vertical asymptote is where, see, this would be the horizontal asymptote. The line comes up and it gets closer and closer and closer, and it can actually cross the horizontal asymptotes, but if it does, it comes back up and rides underneath it. Whereas, and then same thing with this, it could approach it from the left, and that's what this is saying. As x approaches infinity, negative direction, then it reaches that, whatever that horizontal line is, like it could be 1, it'll get closer and closer and closer to 1. Okay, and this would be an oblique asymptote where it's not vertical, it's not horizontal, it's an equation of a line. Like this could be, this equation of this asymptote could be like x minus 3 is the y equals x minus 3. That could be that equation, for example. And so this equation will come up and it'll just ride along that asymptote up there. Find the vertical asymptotes of a rational function. Basically, we're doing the same thing as if we were trying to find the domain. We're going to set the denominator equal to 0 and then solve. And so when we do that, we get x equals to a negative 3. So on this, if you look on the graph, this would be here's negative 3. This would represent the vertical asymptote at x equals to negative 3. So it's like a dotted or line that goes through negative 3. Goes through the x-axis at negative 3. Okay, the next one here, now the denominator you want to factor. Like this could have originally started off as x squared. This could have originally started off as x minus 3 over x squared minus 4, and then when you go to factor it, you get this, x plus 2, x minus 2. And so you set each factor equal to 0. X plus 2 equals 0, and so we get x equals to negative 2, and x minus 2 equals 0. We get x equals to a positive 2. So now in this graph, the vertical asymptotes are going to be here at negative 2 and positive 2. So they'll come down like that. And so that's all we're doing for right now is just looking at the vertical asymptotes. Alright, and so we get our x equals to 2 and x equals to negative 2. So last when we were looking for a domain, notice when we were looking for a domain, we got the same thing. And so when we looked at our graph, we saw that we had this cannot have -2, cannot have +2. Well, that corresponds with our line graph and our domain, where a domain was -infinity to -2 union -2 to +2 union 2 to infinity. So it corresponds with our domain. So when we found that our domain was restricted at -2 and +2, that's because that's where our asymptotes are. All right. And so graphically, that's what that would look like. All right, and then here we have x squared plus 5 plus 4. So we want to go ahead and factor that. And so when we factor that, put our factors there, x and x, plus and plus. Factors of 4 are to give us 5 is going to be 4 and 1. And so we said x plus 4 equals 0 and x plus 1 equals 0. And that's where we get x equals to -4 and x equals to, it should be x plus 1 equals 0. So we get x equals to a -1. So on our graph, we will have vertical asymptotes at -4 and -1. Put -1 in there. And so our domain would be, where that would be not, we cannot have, here's our -infinity to infinity, right? But we cannot have -4 and we cannot have -1. And so those are open. And so our domain would be -infinity to -4, -4 to union, and then -4 to -1, open there, and then -1 to infinity. So again, our domain, our asymptotes also correspond with our domain. Okay. And then here we have this one here, this x squared minus 4 is like this one here, except for this second one is factored out, this one is not. Okay, and so, but now this one is a little different because of the numerator. So here we got x squared plus 3, x squared plus 3 plus 2. So, let me back off a little bit. Back off. There we go. So, if we were to factor the numerator and then factor the denominator, we get x and x, plus and plus, factors of 2 are 2 and 1. Alright, now let's factor the denominator, and that's going to be x plus 2 and x minus 2. Well, we can see that we have an x plus 2 and an x plus 2. And just like with fractions, those factors can cancel. And so that's why we only end up with an x equals to 2 for a vertical asymptote. But for a domain, it would still be, what happens here is this is a hole right here. And so we don't get an asymptote, we would get a hole there. But our domain is still going to be x cannot be -2 and x cannot be +2 because of this other number. Because this, if we put -2 here, we would still get an undefined. But the problem with the calculator, graphing, relying too much on the calculator, is the calculator will not show this hole. You have to know that it's there because of the properties of algebra. Alright. And so our vertical asymptote is just x at 2, and then we're going to have a hole at negative 2. Alright, we'll cover more of that later on. Find the horizontal or oblique asymptote. We have a horizontal asymptote where the leading term for our polynomial, our leading exponent, is x to the n and then x to the m down here. So if our leading exponent is less in the numerator than in the denominator, then our asymptote is at y equals 0. For example, if we have here f of x is equal to, let's say, x plus 2 over x squared minus, let's say, 4. So our asymptote here would be y equals to x over x squared. You only look at the leading terms. And since the n is less, the degree of the numerator is less than the degree of the denominator, then our asymptote is automatically y equals 0. So in other words, looking at it on the graph, it's right on the x-axis. Okay? So when the degree of the numerator is less than the degree of the denominator, then it's right there. Our horizontal asymptote is right on the x-axis. Okay, when the degree of the numerator and the denominator are the same, then you take the coefficients. For example, if we have here y, let's say we have here f of x rather, equals to x squared plus, let's say, 3 over x squared minus 25. Okay, we look at, let's say, and to add to this, redo this. Let's say this is 5 x squared plus 3 over 2 x squared minus 4. Okay, again, we look at our leading terms. So we're looking at y equals to 5 x squared over 2 x squared. Since the exponents are the same, the degree of the numerator is the same as the degree of the denominator, then our asymptote are our coefficients. So our horizontal asymptote, and I'm just going to abbreviate it, is y equals to 5 over 2. So it's just the coefficients of our x squares. So for example, another example is, let's say we had here, we're looking at 3x squared over just 1x squared for our leading terms, then our horizontal asymptote would be y equals 3. Okay? And so on the graph, it would look like this, where y goes through the y-intercept at 3. And then here, when the degree of the numerator is greater than the degree of the denominator, then there is no horizontal asymptote. For example, let's say we had here f of x equals to x squared plus 1 over x minus 2. So this would be x squared over x. There's no horizontal asymptote, but there is an oblique asymptote. And so what you would have to do is you would have to use long division to divide it out. Okay, we'll get to that in a little bit. So when the degree of the numerator is larger than the degree of the denominator, there is no horizontal asymptote. Find the horizontal asymptotes, if any, for the graph. So we would look at this as ax to the n over bx to the m, and so we would look at just the leading terms. This would be x over, we're looking at x over 4x squared. So is the degree of the numerator less than, equal to, or greater than? You should have said the degree of the numerator is less than the degree of the denominator. So therefore, our horizontal asymptote is at y equals what? You should have said 0. Degree of the numerator is less than the degree of the denominator. The horizontal asymptote is at 0. Okay. And so that's what we have here. Oops. That's what it says here. Alright, so and that's all we're doing for that problem, is just looking at the horizontal asymptote. Okay, here we have a rational function. We got polynomial in the numerator, polynomial in the denominator if it's improper, like an improper fraction. Well, an improper fraction is where the numerator is larger than the denominator, like 5 over 2. That's an improper fraction. So that's what they mean, where the degree of the numerator is larger in the numerator than the degree in the denominator. We don't have a horizontal asymptote, and so what we have to do is use division. And what we end up with is our quotient is our oblique asymptote, and the remainder, we just drop that because the remainder just rides along closer and closer to that oblique asymptote. The graph just rides along that. Okay, so that's all that means there. Alright, so find the horizontal or oblique asymptote. Alright, so looking at this, we can see that our degree of the numerator is it less than, equal to, or greater than. Okay, we see that it's greater than. So there is no horizontal asymptote, it's an oblique asymptote. So what we have to do is use long division. Okay, and so we're going to take, and let's see if that's what they do here. Okay, yeah, at this point, alright, now at this point, what they do is they take the denominator, that's our divisor, and we have our divisor as our denominator, and our dividend, that's the numerator. Now notice, for each place, you have to have a place for, like here you have to have a place for the x to the 4th. You need a place for the x to the 4th. And here we need a place for the x to the 3rd. And actually that's down here. And here we need a place for x squared. And here we need a place for x. And here we need a place for our constant. So we have a 3x to the 4th, but we don't have an x cubed. So we could put like plus 0x cubed here if we wanted to. You don't have to, but you could if you want to. And then minus 1x squared, and we could put a 1 there. And then this would be plus 0x, and then plus 0, like that. So we have to have a place for each spot. And so when we do that, we take a look at just the leading term, and we say, all right, what times x cubed will give me 3x to the 4th? Well, we know we got to multiply 3. And if we multiply x times x cubed, we get x to the 4th. So this would be 3 times x cubed, and we get 3x to the 4th. But then we have to multiply 3x times all of the terms. So this would be 3x times a negative x squared, and so this is a minus 3x cubed. And then we got to multiply 3x times 1. Well, there's no x squared here, so we have to leave a space there and put it under the 3x, the space for the x's. Now what we do is we change the sign. We have to multiply everything times negative 1. We've got to multiply everything times a negative, because just like if we had a, let's say 100, well, we know that 3 divides into 10, and that's 3, and we get 9, right? Well, we subtract here. We have to subtract, and that's what we're doing here. And then we, again, put 3 times 3, that's 9. Again, we have to subtract. And so that's what we're doing here. So when we do that, we've got to change the sign. So for everything, this will be a negative, and we're distributing. So this will be a negative here. This will be a positive, and then this will be a negative. So we're distributing that negative into everything. Okay, and so we get a negative 3x to the fourth and a positive 3x to the fourth. We want to cancel out the leading terms. And that's the whole idea. Everything else can carry down, but we've got to get rid of those leading terms. So that's where this 3x cubed becomes a positive. Bring down the minus 1x squared, and then this will be a minus 3x. Now, we look at what times x cubed will give me a 3x cubed. Well, 3 does. So we want to multiply 3 times x cubed, and we get the 3x cubed here. But we can't stop there. We've got to do that to all 3. So this will be 3 times minus x squared will be a minus 3x squared. And then 3 times 1 will be 3. Well, there's no x, so we have to put a space here for the x's. Again, we have to change the signs, right? Make that minus sign a plus and distribute that negative. So that changes the 3 to a minus, changes the 3x squared to a plus, changes the 3 to a minus. So the 3x cubed becomes a negative 3x cubed. So now the 3x cubed is a positive 3x cubed and a negative 3x cubed. They go to 0. That's what we want. And so we've got a 1x squared here and a 3x squared. And that's a minus 1x squared and a positive 3x squared, so that gives us a positive 2x squared. Minus 3x minus 3. Well, since our exponent is an x cubed, we can't divide anymore. And so our oblique asymptote is our quotient. Okay, it's our quotient. And so that would be 3x plus 3. So if you look on the graph, here's 3. It's going to go up 1, 2, 3, and across 1. So our oblique asymptote, we're going to graph it just like we would graph any linear equation. And that would be our oblique asymptote. Okay. And so we use long division to find that. Alright. And so our horizontal, our oblique asymptote is just the quotient, the 3x plus 3. And that's all we use. Alright. Find the horizontal or oblique asymptote. So, from this, we're going to look at our leading terms, right? And they are the same. So therefore, we're looking at the 8x squared over 4x squared. And since the degree of the numerator is the same as the denominator, then we're basically looking at the coefficients, 8 over 4. And so that would give us 2. So when the degree of the numerator is the same as the degree of the denominator, we just look at the coefficients of our leading terms. And so our horizontal asymptote is at y equals 2. So graphically, this would look like this at y equals to 2. Okay. here's our summary. Degrees of the numerator less than the denominator, we get y equals 0. When it's greater than, we get an oblique asymptote. When they're the same, we look at our coefficients to our leading terms.